So within the framework of H2O to University of Coimbra in the work package 4 that is relates with development of advanced and cost-effective treatment technologies for drinking water, the University of Coimbra was working on the development of new materials and technologies to remove pollutants from the water. So in our case, we tested the possibility of using new technologies to remove pollutants before the disinfection step, this way removing the organic matter that is in the source water before disinfection. So this way we are removing the DBPs precursors. So if the DBP precursors are removed before disinfection, or at least reduced, the amount of DBPs that are being produced during the disinfection will be, of course, lower. And we also tested new solutions for the removal of the DBPs from the water after disinfection. Let's say if it's unavoidable to have the DBPs produced, we have also technologies to remove them after their production. So in what regards to the removal of the precursors of the DBPs, we were focused on several pollutants, natural organic matter, but also some contaminants of emerging concern that are now appearing in the drinking water sources due to the contamination coming from human sources, let's say from the municipal wastewater treatment plants that are not able to remove totally all the pollutants. And these contaminants of emerging concern that can be like pharmaceuticals, they can be pesticides, they can be for example also some nutrients and some proteins. They are not totally removed on the conventional municipal wastewater treatment plants, and also they can reach the water sources from the industrial discharges. These compounds are not amenable to be biologically removed, which means that they will accumulate in the source waters, so they can constitute a problem in a medium and long term. So we need to tackle them down. And in this case, we evaluated several technologies like adsorption, using engineered materials to do the adsorption, like aerogels, where the surface of these materials can be, let's say, engineered, functionalized to be specific for the removal of specific compounds from the water. But we also tested some advanced oxidation processes, especially those that are based on the radiation. And in this case, what we are using as, let's say, oxidants or as reactant to promote the oxidation of the pollutants, it's the light. And this is very interesting because if the process is optimized, we can even use the sunlight light to promote that reaction, which will decrease, of course, the costs associated with the treatment process. But for that we need to develop materials that are active to the light, so that they are able to be excited by the light to promote the formation of radicals that are oxidants that are able to remove, to degrade and oxidize the organic matter that we want to remove from the water. And in this case, we tested several types of materials and several combinations of oxidants to optimize the process. And we have some interesting results regarding the removal of either pharmaceutical, but also some amino acids that are currently being identified as contaminants of emerging concern in the drinking water sources. The University of Coimbra was also involved in the development of technologies for the removal of disinfection byproducts from the water, from the disinfected water. And in this case, the most interesting technology to remove them was not the oxidation, because these compounds are already in oxidation state that it's not so easy to further degrade them by oxidation, but we were able to develop some interesting materials that are able to absorb these compounds from the drinking water, and we reached more than 90% of their removal from the water under several conditions. We also evaluated the possibility of using let's say cheap materials to absorb these compounds, and we were surprised to see that, for example, low-cost materials such as sand, that is very used as a filter in the water treatment, is really able to remove at least the 3-allomethanes from the water. And another interesting conclusion that we reached is that these materials are not easy to saturate, which is an important point when we are dealing with absorption, because in the absorption system, since we have a molecule that is being removed from the liquid and is going to be absorbed in the solid is only able to absorb as long as it's not saturated, as long as some part of its surface is still available to receive those molecules. That is called the saturation of the material, and when we reach that saturation, the material needs to be regenerated or substituted completely. And in our case, we studied these materials in a continuous system from several hours, and we didn't reach still their saturation level. These materials were also tested at a pilot scale in a larger unit that was designed and assembled by our partner Adventech, and it was interesting to see that the results that we reached at the lab scale were validated at this larger scale with higher or larger flow rates, which is very interesting, and it's a very important result to further study these technologies and put them into the market, which is very important. Of course, the University of Coimbra is still interested in exploiting these results, and we are further studying other compounds like alloacetic acids using these very same materials, so that we can understand if these technologies that we developed can be extended to remove other types of DBPs from the drinking water.